All right, we're going to do some quick problems here. These should not be too difficult. The trickiest thing that you're going to find, I think, with these types of problems is if you are rusty or concerned about Lewis structures. That could cause you to run into a few problems. We'll try and do a little bit of practice in class, but if you are unsure about the Lewis structure process, make sure you refresh your memories because there will be a couple in which you have to figure out how many single bonds or double bonds or triple bonds are involved, and if you can't draw your Lewis structures, it's a little more difficult to do. So we're going to use the bond energies from the reference chart above/below to estimate the enthalpy change for the following reaction, and then we want to know, does it illustrate an endothermic or exothermic process? Okay, Lewis structures are pretty easy to draw for us on this one. I will sketch out here my Lewis structure for hydrogen, which is just a single bond because they each have one electron to share. Chlorine, on the other hand, although it is also singly bonded to the other chlorine, will have several pairs of unshared electrons around each of the chlorine atoms. And then we're making 2 moles, or I'll draw 2 molecules of the HCl gas here, where again you should recognize that the chlorine will have several lone pairs of electrons that are unshared in its Lewis dot structure. Okay, now that said, we're thinking about in this problem how much energy is going to have to be put in to break these bonds and how much energy is going to be released when these bonds are formed. And to figure that out, we're going to use the equation where the delta H of the reaction is equal to the sum of the enthalpy changes in the in the breaking of those reactant bonds minus the sum of the enthalpy change as the energy is released from the formation of those product bonds. And if we take a quick peek, it's simply a matter of looking at this bond energy chart and plugging it into the formula. The energy required to break that one HH bond, or 1 mole of hydrogen bonds, is going to be 432 kilojoules of energy. We're going to add to that the energy required to break 1 mole of those chlorine-chlorine single bonds, which is equal to 239 kilojoules. And that sum is the sum of the energy that needs to go in to break those bonds. We're going to subtract from that the energy required, or the energy released rather, when those 2 HCl bonds are formed. So note it's going to be 2 moles times the 237 kilojoules that's released as those bonds are formed. And a quick calculator time should end us up with a positive 197 kilojoule enthalpy change for this reaction, which implies that we are talking about an endothermic process. In other words, it takes more energy to break those bonds in the reactant molecules than is released in the formation of those new bonds in the product molecules. Woo! All right, we're going to do just one more. This one's a little trickier or maybe a little easier, just depending on how comfortable you are with Lewis structures. This one gives us the Lewis structures for the tricky ones, which is nice, although be aware that you should be able to come up with some of these Lewis structures on your own. We'll practice a little bit in class, but what will really help, believe it or not, is your nomenclature, especially when we start drawing out some of these organic ones where there's carbon chains, and you know, is it single bond, double bond, etc. So practice. If you struggle with those Lewis structures still, we're going to use the same formula as we did in the last equation. We want to know how much energy is going to be input to break all of these reactant bonds. Compare that to the amount of energy released when we reform all of these product bonds. And so I'm going to first just sum together all of the bond energies that are going to tell me the energy required to break all those bonds. I'm going to have 614 kilojoules required to break that carbon-carbon double bond. I'm going to add that to 4 times 413 kilojoules, which is the energy required to break those 4 carbon-hydrogen single bonds. And I will add to that the energy required to break the 1 fluorine-fluorine single bond, which is 154 kilojoules. Okay, so sum all these together, we end up with 2,420 kilojoules of energy required to break all of those bonds that make up our reactant molecules. However, there's energy that's going to be released as we reform these new bonds. In fact, we could represent that by taking 347 kilojoules, which is the energy that's released upon the formation of that carbon-carbon single bond, plus 4 times 413 kilojoules, which is the energy released upon the formation of those 4 carbon-hydrogen single bonds, plus 2 times X. X being the 2 bonds that are my carbon-fluorine single bonds, which I don't know what the answer is. I don't know what that bond energy is because, tragically, it's been left out of my bond energies chart. However, lucky enough for me, there is an enthalpy change already provided for this reaction, which is negative 549 kilojoules. And as we think about solving the actual question, though, it's just some basic algebra skills to solve for x. It's going to be minus, we can combine these things here and end up with 1,999 kilojoules plus 2x equals negative 549 kilojoules. And then we'll distribute this negative, so we're going to end up with something like, over here we're going to get 421 kilojoules minus 2x, again after we distribute that negative, equals negative 549 kilojoules. Then go negative 2x equals negative 970 kilojoules. Divide each side by 2x, we end up with x equals 485 kilojoules, which is the bond energy for a single mole of carbon-fluorine single bonds.